Thank you very much for coming here. So today I would like to talk about compact binaries and multi-messenger, which means gravitational wave and electromagnetic counterparts, two messenger astronomies. So it's a multi, okay? So this is outline of my talk. I will give some brief introduction, and then I will talk about major simulations and what is our process Kilonova that we discovered in 2017. And I also talk about the Afterglow, particularly radio Afterglow observation that I have been involved in. And then I will talk something completely different, not completely, but somewhat different, that origin of the binary black hole merger at end. So here, so as you know, the neutron star mergers are a strong gravitational wave emitter. So at the late in spiral phase, we expect to see these strong gravitational waves. And actually, this in spiral waveform is quite beautiful. I mean, can be calculated by GR. It's very nicely and beautiful. So from this waveform, we can measure, for example, stellar quadrupole moment of the neutron star, which allows us to study high density matter in the neutron star. And also, if you can measure this amplitude of the gravitational waves, we can learn about the distance to the source, which allows us to measure, for example, the Hubble constant. So one motivation to study neutron star merger is to study about the fundamental physics. And another important aspect is the neutron star mergers have been considered as a main site of the R process production. So here I show the figure from famous paper B squared FH. It's already 60 years ago. This figure shows the log abundance as a function of atomic mass. And you can see these light elements are produced in the star, and for example, iron group are produced in the supernova explosion. And beyond iron peak, we still have some heavy elements divided. It's classified basically R process, S process, and there are 3 different peaks here. And always R process peak comes a little bit before the S process peak. This has some physical reason. And still we don't know what kind of astrophysical site really forms this R process elements, especially in the solar system and the galaxy. And so far competing scenarios, one is supernova explosion may produce R process, and the neutron star merger also quite appealing site of the R process. And for example, we know from several R process observation like ultra-faint dwarfs and also geological plutonium abundance measurement, the rate so far we know the rate of the R process production should be lower than 1% of the core collapse supernovae. So R process production should be quite rare event, which consistent with the merger scenario. Neutron star merger occurs quite rare in the galaxy. And of course, the big step forward had occurred in 2017 was the first discovery of neutron star merger in gravitational waves as well as the electromagnetic signals. So here I show the time sequence, what happened in this August 2017. First, LIGO saw the gravitational wave signal. This is sharp mass, it's neutron star merge, something like this. And immediately after the merger, Fermi and the integral saw some weak gamma ray pulse. This is sort of look like short gamma ray burst that we familiar with. And half a day after the merger, we started to see optical and UV and near infrared. So the discovery made also included here the LCO discovered the optical counterpart. And also it's interesting that around a week to 2 weeks after the merger, we started to see also X-rays and radio. These counterparts continuously rise since like 2 weeks after the merger and up to 150 days after the merger. So I will discuss these electromagnetic counterparts. So now I'm going to discuss about simulations. So first I would like to show neutron star merger simulation. This is full GR, and but solving hydro, not including magnetic field and neutrinos. So here I show density evolution of the two neutron star. Here equal mass, and this is the emitted gravitational waves. So due to the gravitational wave emission, this neutron star spirals in, and the amplitude and frequency of this gravitational wave increases, and now two neutron stars merge. And in this case, the mass is not that high. The total mass is not that high, so this result leads to our formation of massive neutron star, not immediately collapse to a black hole. So these massive neutron stars still continuously emit gravitational waves, and amplitude gets smaller, but it's still emit gravitational waves like a tenth of millisecond time scale.
Were these tidally locked for this case?
No, it's not locked.
It's not
Yeah, irrotational. Yeah, right. Yeah, I know you showed many years ago that it's not tidally locked. Yes. So yeah, it's currently the common assumption is these are not tidally locked. So because this calculation can give you the gravitational wave signal at late time, so here I show how this merger affected by the tidal effect. You don't see quite large deformation of the two stars, but actually they are deformed by the tidal field each other. And actually you can see the deviation from point mass gravitational waves. So this is, I show you the gravitational wave amplitude as a function of frequency. This is gravitational wave spectrum. So lower frequency means early in spiral phase where the separation is large, and then in spiral goes this way. It's kind of correspond to the time. And here I show the black hole, binary black hole case with the same mass. So if there is no ties, then gravitational wave spectrum should be something like this. However, for neutron star merger cases, so I show here the different equation state. And for less compact binaries, so which means large radius of which tidal effect is strong, then such gravitational waves deviates significantly from the binary black hole merger waveform. And this degrees of the deviation depends on the size of the neutron star.
So to get that signal to noise, would you just require a super nearby then?
Yes. So we show this based on this kind of simulation that what is required to measure the tidal deformability, which is about SN20. Right? Yes.
What was the signal to noise of the Kilonova signal?
Yes, it's actually higher than this value, so that LIGO actually already able to measure this size. And this size is characterized by a single parameter which called the tidal deformability parameter. This parameter characterizes the strength of the tidal interaction, and this way, basically the neutron star size is larger in this way. And this is a result from GW17 from the just gravitational wave data. So here is the posterior distribution of both. This is corresponds to the size of the one neutron star and the second neutron star. So here roughly correspond to the radius of about 12 kilometers, which is sort of small neutron star equation state. And here you can see 90% confidence level. I mean, credible region is here. This is 90%. So for example, the equation states which result in 14-kilometer neutron star is sort of ruled out with a confidence of 90% level. So this is very nice. And we now know the neutron star merger is somewhat small. Okay. And not only the in-spiral phase, numerical relativity simulation can deal with the post-merger dynamics. So post-merger remnants, we have several different evolutionary paths. So one of which is if two neutron star masses are sufficiently small, then this just go to the stable neutron star, which can be supported by either nuclear force and rotation of the fast spinning neutron star. And if two neutron stars have sufficiently massive mass, and then it's immediately collapsed to a black hole. But we have also intermediate case between the stable neutron star and black hole formation, where we have some sort of short-lived hypermassive neutron star, which is supported by differential rotation of the post-merger object. And when after the differential rotation dissipates, it collapses the black hole. And we expect different three cases, like supermassive neutron star or massive neutron star, and hypermassive neutron star case, and direct black hole formation case. And we have performed many set of the numerical merger simulations and figure out what is the typical outcome of these mergers. So here I show you these different nuclear equation state. So here the more small equation state, like radius is 11 kilometer to 14 kilometer, and the total mass is from 2.7 to 2.9. And you can see some variation, like change a little bit to the masses, then you get black hole formation, and this region you get hypermassive neutron star, and below like 2.6 you get supermassive neutron star for this specific equation state.
Is this table sensitive to your assumptions or lack of treatment of the neutrino physics?
This is not that sensitive, but in order to get lifetime of the hypermassive neutron star correctly, it's sensitive to the neutrino physics. So just after the merger, it's okay, but if you want to ask how long does it survive, then neutrino physics and also magnetic field is important. So for gravitational, this GW17, we know where is the mass range of the total mass of this binary neutron star, and from tidal deformability, we have 90% confidence level of some constraint on the equation state. So for this specific event, we sort of expect some hypermassive neutron star is formed at least few milliseconds or 10 milliseconds. But we want to know we want to confirm this fact from other observations. And now I'm going to show, so this is about remnant object, but also the neutron star merger produce some mass outflow when two star merge. So now I'm going to show dynamical mass ejection process. So here I take like 1.3, 1.6 solar mass binary, and because of the mass ratio, one of the light neutron stars is disrupted by this tidal force, and this tidal force ejects some material. In this case, the total mass is sufficiently heavy, and outcome is a black hole. So now you have a black hole surrounded by accretion disk. So this mass ratio and heavy case, so you get prompt formation of the black hole, and mostly the ejecta is driven by tidal force, and the mass ejection lasts about 1 millisecond, and mass is about less than 1% of the solar mass, and velocity of the ejecta is about 20% of the speed of light. And here I showed less massive, like 1.5, 1.2. Here I get hypermassive neutron star at the center. So when we have hypermassive neutron star, then not only the tidal force, but also the shock between the colliding neutron star drives some mass ejection. So in this case, we have tidal ejecta and also the shock-heated ejecta, and the ejection also lasts a little bit longer, and mass is about comparable for both cases.
Are you going to say about like what's actually in these simulations, or are you treating radiation?
Oh yeah, this is a purely hydro simulation, so it's just a dynamical process, just shock heating and tidal ejecta. So on top of this amount, we expect some additional ejecta due to the neutrino-driven wind and also the magnetic field. So I will discuss a little bit later. So this is the dynamical eject just you can get from tidal force and also the shock heating. So this dynamical ejecta mass, and vertical axis shows the disk mass, how much disk mass I have. So for different points shows different parameter of the simulation. And I think I will come back to this point later, but the important point is the dynamical ejecta that we can get from numerical simulation is always up to 0.02 solar mass. We never see much more mass ejection unless, I think, the neutron stars are tidally locked or highly eccentric orbit. And disk mass can be larger than the ejecta mass, like disk mass can be more than 10% of the solar mass. And depending on how large fraction of the disk ejected from this system, I can get more than dynamical ejecta from the disk outflow. So currently the theoretical picture is something like this. As I showed you, there is some mass ejection due to the tidal force and the shock-heated ejecta, which we call dynamical ejecta. And post-merger phase, we also have some neutrino-driven wind from post-merger object, and also the disk wind is also expected. And even after the black hole formed, and then it's still surrounded by massive accretion torus, and which drive the wind. So before this gravitational wave event was discovered, we were not really sure that which one dominates in mass budget, but I will discuss later but which one. Now what is the current picture of these different components. So now I want to proceed to our process Kilonova. So this is the Kilonova that observed after GW7017. So this is Kilonova. Look like it's very rapidly evolving. So the brightness is, so this is magnitude as a function of time, and the peak luminosity is much fainter than the supernovae that we usually see. And also time scale is much different. So time scale of the supernovae are longer, and the Kilonova time scale is much faster, which is consistent with the picture that the ejecta mass is small and also the expansion velocity is fast. So it's everything evolves quickly, and also the peak is not that bright. So the picture behind this Kilonova is something like this. So Kilonova is actually proposed many years ago by Lee and Patinsky, and then improved by Shuri Kulkarni and also Brian Metzger. Now the current picture of the Kilonova is something like this. So first, two neutron star merge, and the dynamical mass ejection occur. This is the scale of 10 kilometers. And then post-merger object also ejects some mass, which may last about 100 milliseconds. And the scale is about 10 kilometers to 100 kilometers. And inside this expanding ejecta, it's composed of quite neutron-rich material. And free neutrons are just absorbed by heavy elements. And this process occurs much faster than the beta decay, so we call our process nucleosynthesis. And this process occurs maybe less than 1 second. And the size scale is already, ejecta expand already, about 0.1 solar radius. And still this ejecta is expanding and expanding, and the size of the ejecta gets bigger and bigger, and photon can diffuse out. And because these Arbros elements are initially radioactive, so continuously provide heat to the ejecta, and we see diffusing out photon as a Kilonova. So this is brief picture of the Kilonova. So this is show how much Arbros elements you get after the neutron star merger. Here, the neutron number and proton number. And what is important here is because of the ejecta is so neutron rich, almost all the material goes to the heavy elements. You can see little abundance in the light elements, but most of the elements are in the heavy elements. And these are the just final snapshot of our process nucleosynthesis. And these squares, black squares, show the stability valley, stable elements. And these are heavy elements and radioactive, so they are unstable. And then these unstable neutron-rich nuclei decays toward stability valley and release energy. So this is the energy source of the Kilonova. And here, this is the famous power law radioactive heat after the neutron star merger. So this is radioactive power per unit mass as a function of time. So it goes beautifully like t to the minus 1.3. And this is actually, this doesn't really depend on the exact composition because there are so many different species contributed statistically, and you can get some robust power law, and normalization is also robust. But actually, in order to calculate heat, the exact composition doesn't really matter. But in order to calculate what kind of photon we see depends on the composition. So here again, the R process, solar R process abundance as a function of atomic number. So here first peak, second peak, and third peak. And between the third peak, we have sort of weird elements called the lanthanoids. So these are sort of special elements that makes difference in the radiation transfer in neutron star merger. Right? Yes.
Just explain what are the physical elements that make the prediction on the previous slide so robust? Not the, yeah. So
Oh.
and then right here, why is the normalization so well understood as well as the decay? Can you just explain what the basic physics is?
The basic physics is the weak interaction. So we know, for example, d and dt, let's say, okay, d and dt, the lifetime is distributed like a constant number of the radioactive species in the each lifetime scale is constant. So d and dt goes like 1 over t. And the question is, what is E, which can be calculated by the Fermi theory of the beta decay. And
How do you know how much material is participating in this?
oh, how much material? Yes, this is per unit mass.
Ah, okay.
Right. So you have to multiply
Fine.
total mass.
Yeah.
And
I didn't see the previous mass.
right, sorry. Yeah, so it's per unit mass is robust.
Right, yeah.
Right. And
So that's just nuclear physics.
it's nuclear physics. It's a weak interaction. I mean, the Fermi theory of the beta decay. So, right, yes. So as long as many species join the heat, then you can get a robust heating rate. But here, the question is how much lanthanoid do you have in order to calculate photon transfer? So reason is something like this. So this is, imagine the ejecta is expanding and photons are diffused out, and here is photosphere, and beyond photosphere, it's just escape. But what this determines this diffusion process is the atomic transitions. And here I show the atomic levels for the singly ionized iron versus this is one of the lanthanoid element, the neodymium, singly ionized neodymium. So you can immediately see how dense is this atomic levels. And this dense atomic level leads to a significant enhancement of the opacity. In fact, the opacity is different by a factor of 100. So it's very hard to escape for photons in this lanthanoid-rich ejecta. And we showed actually, we include these lanthanoid elements in the radiation transfer to show, for example, if you have only iron opacity, the Kilonova light curve look like this. So peak around half day, and then luminosity is quite high. But if you composed of full of R-plus elements, this reduced to this black curve. So including this large, many transition lines reduce your peak luminosity, and your peak time scale will be longer.
Where did the cross sections come from? For all these transitions?
Yes, so this is this is the result of the radiation transfer, including these transitions. And to get this sort of bolometric luminosity, you figure out the cross section should be about 10 square centimeters.
Where do you get the atomic data?
Oh, atomic data.
Data for not neodymium or whatever it is.
Exotic things.
We use some available open database, like Kurtz database, Baldo database. But you can see here is completeness of the lines. And we don't have highly ionized atoms for the opacity calculation. It's sort of limited, but we include as many as possible. Right, so...
Excuse me, why is
Here?
What, 80, 84?
This is biased because of the solar abundance. They are unstable, right? They are unstable against alpha decay. So initially there should be elements here, but they decay. And because of these are mainly experimental data, so we don't have good experimental data here. Is it?
You create a Kilonova in the lab.
I mean, they're around for, some of those elements are around for 1,000 years.
Mm-hmm.
And you look at the afterglow.
Right. We should have these elements in the Kilonova, but this we just omit because we don't have in the solar system. This is just our issue that we didn't really choose this. And currently, people try to get more data from just theoretical calculations of the atomic structure. Now I want to compare this is Kilonova GW70 of 17. Here, the total luminosity as a function of time. And these are bolometric data taken from this paper. And this is just beta decay power. This is radioactive power in the neutron star major ejecta. And initially, because this is optically thick, you don't really see total power of the beta decay. Because of diffusion process, it's suppressed. And then afterward, the photons start to diffuse out. And in the end, this photon luminosity equaled to beta decay. Yes?
So those ground points are maximum correcting you're applying a bolometric correction to the infrared and optical observations?
Yes. So the last two data points are not bolometric corrected data. It's just new from Spitzer data. So I want to emphasize here, in order to explain this observed luminosity, the beta decay heating is quite works well. So this is one of the evidence that we really see many nuclear decay chain which can really match this bolometric data. And second important point is the peak luminosity is quite high, and as well as the luminosity late time is quite high. In order to explain this high luminosity, you need like 5% of the solar mass, which is, I would say, it's more than expected before the event. And
You said you couldn't get ejected that are more than...
Yes, exactly. So this is the point that it's quite high. And in order to explain we might miss the peak of the rise. This should rise at some point, but we probably miss the peak. And this fact tells us the opacity is somewhat small. If the ejecta is fully composed of process elements, we expect something this kind of flat and slow rise light curve. But what actually we see is something this sort of behavior that probably at least some ejecta material like here or line of sight material of the first component composed of the not that heavy element.
So, but how are you able to predict when it becomes optically thin?
Oh yeah.
Isn't the argument that this is beta decay basically what you're seeing?
Yes, this is beta decay. Yeah, I just draw such. So actually, I will talk more details tomorrow. If you will be here, and I will explain more. Okay. So the immediate implication of this bolometric luminosity is here. So as I said, the required mass is about 5% of the solar mass, and none of the numerical relativity simulation reproduce the dynamical ejecta mass, the above 0.05. So
maybe we'll talk about this later too, but is that sensitive to any assumptions about isotropy or the geometry of the event?
I think it's not that significantly affected, because anyway, this is sort of slowly expanding, and geometrical collection is, in particular later time, is quite small, I would say.
Kent, I'm kind of curious, you know, if you look at this from somebody who's been worrying about type 1a supernovae, where we still debate the ejected mass by 50%.
Oh yeah, yes, yes,
40
yes.
years of data.
Yes.
You have, I'm wondering why, I mean, it could be the opacity is wrong by a factor of 2, right?
Right.
And your mass would be different by a factor of 2, or am I missing something?
All right. Yes, so here, okay. So
It would be even more opaque and it's less mass. If you
right, so here, okay, the mass 0.05 is coming from sort of late phase, I would say.
Okay.
And if you change the opacity factor of 2, you change,
When it becomes out to be
right, here.
total energy, which it shouldn't depend on the opacity.
Right, the total energy, so you start to see most of them ejecta at later time, where opacity is not really affects the light curve.
But when you fit for that 0.05, what data informs the fit? Is it just the late time behavior such that it's robust?
Yeah, I use this sort of total, all the points. But you can see, in order to make this luminosity at later time, you need anyway some this is 0.05 solar mass in the beta decay.
I'm not seeing the t to the minus 1.3 from that data. It's a
Uh,
lot steeper.
You may be right. Where? From?
Well, I'm just
It's
saying,
about it minus 1.3 actually. Let me see.
that's the red curve.
Yeah, red curve, yes. Oh, blue.
Ah,
So blue is not heating rate, but it's after taking into account the diffusion of the photons.
there's a convolution going on.
Yeah. So yeah, it's not really the bolometric data follows t to the minus 1.3.
But sorry, to get back to Lars's question, isn't the ejecta mass is basically determining the overall amplitude of this?
Yes, and also yes.
Okay.
And also the combination of the opacity, velocity, ejecta mass determine how quickly rise the shape of this rise. Right, so it's degenerate with the mass and velocity and the small opacity at the outer layer material. Okay, so yes. Now, okay, I talked here. So we think this possible explanation of this 0.05 solar mass is due to the disk wind. If the disk mass is more than 0.1%, 10% of the solar mass, then it may be possible to get like 5% of the our process mass production here. So after this event, in the community, the current standard picture, I would say, is dynamical ejecta is sort of minor contribution in terms of the mass. And we think this post-merger disk wind contribute much, like 5% of the solar mass. So this is what we have so far. Now I would like to proceed Afterglow jet. So, okay. So far I talked about Kilonova, which is, so this is again the flux density and time. So Kilonova is somewhere here. So we see optical to infrared band. But we have seen this X-ray and radio rising from 10 days to 2 weeks to 100 days. And then it turns to be fainter and fainter. So these are different components. We call this afterglow, which is driven by the kinetic energy of the outflow and make this kinetic energy converted to the shock energy and then radiated away by the synchrotron radiation. So this is completely different story. This is driven by radioactive. Kilonova is driven by radioactivity, but afterglow is driven by the kinetic energy. So now the main question after we see this afterglow was do we see a relativistic jet or something like spherical dynamical ejecta? What really produced this afterglow? So in order to answer this question, we have conducted this VLBI radio observations in order to get image of this radio afterglow. And the hope was to see this kind of jet-like image, but the reality is not so good. But so it's something like this. So it's not look like jet, but this is yes, we used the radio telescope array in North America, and so actually this is consistent with just beam pattern, which means we didn't really resolve the source. We knew this. It's very hard. It would be very hard to resolve this afterglow, but it's surprisingly small and consistent with the unresolved source. But it was lucky for us because we had a two epoch observation. One take like 75 days after the merger, and another one 230 days after the merger. And it was surprising that actually this source was moving. This is the radio emission region at day 75, and this is 240 days after the merger. And actually the shift of the centroid is about 2.7 milliarc second in 150 days. And we know the distance to this galaxy is about 40 megaparsec, and this angular shift is about 0.5 parsecs. And the motion 0.5 parsec in 550 days, you can estimate what is the apparent velocity of this radio emission source. And it is about 4 times the speed of light. This was quite surprising. This doesn't mean this source is actually moving faster than speed of light, but this means the source is moving relativistically, so that apparent velocity can be faster than the speed of light because of the photon traveling effect. So the Lorentz factor of this motion requires at least Lorentz factor more than 4, and source is actually not resolved. So this means this two fact means the very strong evidence for the jet, which is collimated. So if it's extended, we expect some bigger image, but it's very small, and this is also moving relativistically. So we can conclude that we saw the relativistic jet from this event. So now I want to show you some nice animation made from our collaboration. So now I'm going to show the physics picture that can explain the afterglow data consistently. So here, off. So here, the neutron star merger ejecta is surrounding the jet launched from inside the neutron star merger remnant and expand into this expanding ejecta. So here is expanding ejecta here, and then this jet penetrate in the ejecta. And now this breaks out from the ejecta. Right. And
so how did you get the Earth viewing angle there?
oh yeah, this is one is from superluminal motion. In order to see apparent velocity is 4, you have to be right viewing angle.
Right.
So this is
that gives you a constraint.
Right, constraint. And also I have light curve shape, which also have some information of the viewing angle. So now this start to, now it doesn't look like jet, but now it's relativistic shell. So it's more like blast wave expanding into the ISM. And at some point, the interaction with the ISM is significant and then start to produce the synchrotron radiation. So it's homologous expansion up to here and start to interact with the ISM. So here it's going to show the hydro simulation, the energy density, and here is the resulting synchrotron radiation in the image. And this is afterglow data and theoretical calculation. So this observation angle is about 20 degrees. And actually this shift of the centroid is consistent with the VLBI observation. and also the afterglow light curve, also consistent with the observation. So now we think there is a jet inside in this GW70
Can you remind me what the beam width was? So go back. Or never mind. But, I just wanted to see what the beam width was compared to your simulated observation.
Beam size.
Yeah, the beam size. Yeah.
Yes, it's actually right. Its simulation image, I think, extends something like this. It's very hard to resolve. And what we initially wanted to do is make different images from theory and compare to the observed image, because we didn't really expect this significant superluminal motion. But what in the end we get is a point, very small source, and it's moving very fast. Okay, now, after this VLBI observation, combining with light curve information, we can get, for example, the viewing angle is about 15 to 25 degrees from the axis of the jet. And jet angle is pretty small, like less than 5 degrees. And for example, we can estimate the total energy in the jet is 10 to the 49 to 10 to the 50 erg. And the density is quite small, like 10 to the minus 4 to 5 times 10 to the minus 3 per cubic centimeter. Even though this merger occurs just 2 kiloparsec away from the galactic center, but the density is somewhat very, very small. And because we saw jet, we would seen a strong jet if we were on axis. And because we can measure the viewing angle well, so H0 measurement can be improved by a factor of 3. Yes.
Sorry, does that mean that the H0 measurements that have been quoted you think are too pessimistic by a factor of 3? Meaning you can do better than what has been published so far with H0?
I mean, H0 measurement from just gravitational wave is improved by factor of 3, because just from gravitational wave, we don't know what is the viewing angle. So the uncertainty is improved by factor of 3, including this. Okay, and actually this energy is quite large. Okay, let's go. The last part, I will change some topic. I think I have about 10 minutes or something like this. So the last part is the origin of binary black holes. So far, we have seen one neutron star that we have talked about, so one neutron star merge. But we have also 10 binary black hole mergers so far detected by LIGO. So from about 10 solar mass, and more massive one has like 40 solar mass, so 10 solar mass to 40 solar mass black hole mergers. So the main question is where they come from. And so far, we have several different scenarios that maybe they form in closed binaries and evolve to binary black hole and then merge. And also, dense cluster system can dynamically form the binary black holes. And also, active galactic nuclei is also the appearing site to form binary black holes and maybe primordial black hole as well. So now I want to focus on this question that how the spin parameters that can be measured from LIGO is useful to think of these formation scenarios. So some of you may have heard about binary evolutions and binary evolution synthesis starting from the main sequence to follow all the way to the binary mergers. And this involves a lot of physics which are unknown, uncertain. But I want to take different methods that starting from what we see in the LIGO and try to guess what happens just before the black hole formation. So the question is something like this. We see some binary black hole mergers and just ask what can be the progenitor just before the black hole is formed. For example, there can be main sequence. Theoretically, we don't really expect main sequence stars collapse a black hole, but let's think this possibility as well. or blue supergiant binaries, or red supergiant binaries, or some Wolf-Rayet binaries. So one immediately thing you can rule out is this possibility. The red supergiant cannot be a progenitor just before the black hole formation because they are too large. And if you write down the major time due to gravitational wave, so this is major time due to gravitational wave emission is 10 gigayear at 30 solar mass with separation of 44 solar radii. But red supergiants have much larger radius than the required same major axis, so you can immediately rule out this possibility. So we can have these three possibilities. Now, I want to use this parameter we call the chi-effective parameter. Let me define this chi-effective parameter. So chi-effective is the effective spin parameter. This is a mass-weighted spin parameter aligned to the orbit. I mean, there are two black holes. Each one has spin vector, like chi1 and chi2. And take the component in this orbital angular momentum direction and average with some weighted by some mass of two black holes. So chi-effective can take like -1 to 1. For example, if you have maximally spinning two black hole completely aligned with the orbit, you have chi-effective of unity. And then you have also this completely misaligned case, you get the negative chi-effective. And if two black hole has this kind of spin, you get chi-effective of 0. So this can be measured by the gravitational waves. So what was the measurement? This is a measurement for the first event. So this is consistent with 0, plus minus 0.6. Actually, this is low. I'd say that both spins are low, or both spins are lies on the orbital plane. And why I say this is low? Because the typical massive main sequence stars have a fast spin, of which stellar spin parameter is about 10. So just if the angular momentum is conserved to a black hole, then probably such black hole is rapidly rotating. And even the sun has spin parameter about 0.2, which is even larger than the binary black hole have. So this binary black hole of the first event has a low spin.
Is that 0.2 with respect to the disk, like the solar system disk?
No, this is angular momentum of the sun. Okay. So now I want to use this discussion that tidal synchronization. I have 5 minutes, yes. If you have a closed binary and if the separation is sufficiently close, like Moon and Earth system, one of the star or both star may be tidally synchronized, and where the spin orbital angular frequency is equal to the spin angular frequency is equal to orbital angular frequency. This is aligned to the orbit. So now the question is, for black hole binary progenitors merged within the Hubble time, their progenitors are synchronized or not, and if synchronized, what the expected spin parameters. So now I can estimate the synchronization timescale for different progenitors. And these main sequence and blue supergiants are quickly synchronized within their lifetime because their radius is too large. And they are synchronized, and spin parameter is usually exceed more than unity. So these are unlikely the fact that observed spin parameter is much less than unity.
This is just tidal dissipation?
Yeah, this is just tidal dissipation time scale. Right. And only remaining solution is Wolf-Rayet binary is not trivial, that they are not always tidally synchronized, and spin parameter can be 0.1 or unity, even they are tidally synchronized. So here I want to discuss a little bit more about Wolf-Rayet binaries. So if the separation is much more than 45 solar radii, I'm not really interested in because they don't merge within Hubble time. So there are two cases. One is the same major axis is about less than 20 solar radii. It's tend to be synchronized, and more larger Wolf-Rayet binaries doesn't really lead to synchronization within the stellar lifetime. So using this sort of tidal synchronization argument, you can calculate what is the spin chi-effective parameters. So this is cumulative fraction of the spin parameters. So your Wolf-Rayet binary in a very close separation leads to this high spin population, and the wide binary is sort of 20 solar radii to 45 solar radii composed of this low spin contribution. So we expect some fraction in the low spin parameters and some fraction in the high spin parameters. So this is our expectation. This is one tidal synchronization model, and these are some sort of cumulative distribution of the binary black hole observed in O1 and O2. The important thing is, so far we don't see any binary black hole with definite negative chi-effective. So within the error bar, all the black holes have positive chi-effective. And two of these black holes have a definite positive chi-effective parameter with a 90% confidence level. So it's sort of pointing to the tidal synchronization scenario to explain the origin. Right? Do you have a?
Yeah, well, please finish your thought, then you have a question.
Okay. So, and still I think we cannot really distinguish between this kind of model and isotropic distribution. Still, we cannot really distinguish, but after we have 100 black hole mergers, I think we can distinguish these two kind of scenarios. And last thing is, if you go to the high redshift, because then for the high redshift mergers, the separation of the binary black hole progenitor should be close because merger time is shorter. So here I show the low spin mergers population goes down if you go to the high redshift, but high spin mergers start to dominate over the low spin binary black hole mergers. So yes, let me stop here, and I want to take questions. Thank you very much. Yes.
So how sensitive was your argument about the Wolf-Rayet distribution of spin parameters to the unknown tidal dissipation quality factors of those stars?
Right.
That a big problem, or is it not a big deal?
It's big deal. It's big deal.
Okay.
We don't know several things. One is also tidal dissipation and also wind.
Yes.
So these two are uncertain, and if you change this rate, you get more high spin or small high spin fraction. So this here is shifting with these unknown parameters. Here I just choose one parameter to get somewhat.
So it's consistent, but you would say that the tidal scenario doesn't really offer any kind of definitive prediction here because those uncertainties are so large.
Right. So the definitive prediction should be aligned spins are positive and somewhat bimodal.
Yeah.
That's some robust, but quantitatively it's very difficult.
So is it obvious that the black hole binary just simply inherits the chi-effective of the Wolf-Rayet progenitors?
Do you mean it's okay?
Like you have to collapse to the black holes after you have these stars.
Right.
Is it obvious that
It's not obvious, and
doesn't involve changing?
right. So far our understanding is that if the spin parameter of the Wolf-Rayet is less than unity, then almost all the material goes to a black hole. In this case, angular momentum is conserved and chi-effective is conserved. But the question is, when you get chi-effect spin parameter larger than unity, then it's non-trivial how much goes to a black hole and how much is ejected. So, but this matters for high end of this distribution, right? So this is one thing that sort of we don't know, and we also assume that binary black hole hadn't obtained any additional angular momentum from accretion after the formation. That's the assumption as well.
That seems plausible.
So are the predictions for the jet afterglow sensitive to the surrounding ambient medium? You said something
Yes.
about running into the ISM, but you think it would run into the ejecta from the stellar winds when the stars were on the main sequence, and that density distribution would make a big difference in what you see.
Yes.
Have you explored that, or what do you assume for the predictions?
Yes. So, right. So, usually for neutron star mergers, we believe that neutron star merger occurs very long time. I mean, there is very long time delay between the formation of the binary neutron star to the neutron star merger. So we don't think there is remaining stellar wind around the neutron star merger. So what usually we assume is constant ISM density surrounding around the neutron star merger, and we pick up some constant value. But signal is really depends on this, how much you take. And from, for example, actually, I don't have, right. So this is, we can estimate, for example, energy over density from the, when is the peak of the afterglow light curve time scale. And this is, and if you change this density, for example, it can be unity, right? This ISM density can be unity. If you use unity, its afterglow is much brighter than what we see in GW1717. Right, so
5 times 10 to the minus 3 is that's like diffuse hot ISM then?
yes, it
Seems like
looks,
very low density for an ISM like density.
yes. Right, so I'm still wondering why.
That's like the halo gas density.
Right. But the offset from the galactic center is about 2 kiloparsec. So I don't know why that low density, but yes, it's something going on to stripe maybe the ISM in the stellar disk that we don't really know.
So you have to be like inside some hot bubble,
Maybe.
or kicked into the halo, one or the other. So
Yeah, it's projected distance, so it can be something like kicked out in this direction, line of sight direction. Yes.
So you didn't say much about the short gamma ray burst. What does the time delay between the gravitational wave event and that burst tell you?
It's about 1.7 second.
Right.
And this time delay tells you the combination between the jet formation at the time delay between the merger and jet formation, plus how long does the jet propagate inside this ejecta. Because this gamma ray should,
The ejecta now being the
dynamical ejecta. And we believe, we believe this breakout of some shock made by this jet and the ejecta interaction produce the gamma rays. And 1.7 second is, I think, dominated by the propagation effect inside ejecta. And it tells you how big is the ejecta when the shock breaks out from the ejecta. So, and so also I want to say this GRB that associated with merger event, the energy is very low compared to the normal short GRBs. And also this energy is much lower than the energy we estimated from this afterglow observation. So we haven't really understood what's going on.
This is not a viewing angle.
Yeah, that's the question. Is this corrected for it's off axis?
This is not likely the effect of the viewing angle, because if you do Lorentz transformation or say Doppler transformation of one of this, you also goes down energy, but also goes the spectral peak like this. So simple Lorentz transformation gives you somewhere here. You get the low energy, but at the same time, the spectrum peak is Doppler shifted. You cannot do this way. So it's very hard to reconcile just simply off-axis model.
All right, let's thank Kenta.
Thank you.